Hello viewers, Wagdaruna taking you through the story of A-Level Physics Paper 2. And this video I'm going to go through the part called Dielectrics in Capacitors. So this video is under Capacitors and is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we start, let's first look at the course outline for this paper. So physics paper 2 is divided into 4 parts. The first part is geometrical optics, where 2 questions come from these topics and the student must answer 1. The next part is physical optics, or what we call waves, where 2 questions come from these topics and the student must answer 1. The third part is electrostatics and electricity, where 3 questions come from these topics. And the fourth part is magnetism and alternating current, where 3 questions come from these topics. So it is you to choose. You can choose to answer 2 from here and 1 from here to make the 5 questions which are required, or you answer 1 from here and 2 from here. Any is okay. So far we have covered a number of parts. The first part was covered, second part was covered, third part was covered, fourth part was covered, fifth part was covered, and now we are going to cover the last part in this topic, and that will be dielectrics in capacitors. So we're interested in calculations, but the notes are available in this book called Mastering A-Level Physics Paper 2. It contains clear notes, worked examples, and trial questions of all the parts of Physics Paper 2. So our interest on this YouTube channel is the worked examples found in this book. Other books are also available. For example, if you do physics, then you need 3 books. The first book is this Physics Paper 2, the next book is Physics Paper 1, and the third one is the Topical Question Bank. That is if you do physics at A-Level. If you do math at A-Level, you need Math Paper 1, you need Math Paper 2, and you also need the Topical Question Bank. Then if you do subsidiary math, you need this book of A-Level, Mastering A-Level Subsidiary Mathematics. And if you're at O-Level, there is this Topical Question Bank for math, and also these 2 books for physics. So if you need any of these books, you can contact the author on these contacts. So now we can start our topic, dielectrics in capacitors. So in simple terms, a dielectric is an insulator. So they are the dielectrics in capacitors, they are used to separate the plates of the capacitor and to reduce the chances of electric breakdown when a large PD is applied. So previously we have seen capacitors are represented in this form, and this in between the plates was air or free space or vacuum. But now in this case we shall need to put what we call an insulator or a dielectric and the reason is to reduce chances of electric breakdown when a large PD is applied. And also another advantage is to separate the plates. But more of the advantages are found in the notes of Physics Paper 2 in that book. So when they talk about a dielectric, this is what they mean. A dielectric material is placed in between the capacitor plates, and dielectric in simple terms is an insulator. So you can define it as a material which has no conductible charges. It must be an insulator and is able to withstand high electric fields before it breaks down. And the reason is because of this, because its one purpose is to reduce electric breakdown. So it must be able to withstand high electric fields before it breaks down. Some of the examples can be glass, polythene, fur, wool, etc. As long as it's an insulator and it's able to withstand high electric fields, it is okay. So there are some terms which we also need to know. One is dielectric strength. So what is a dielectric strength? So dielectric strength of an insulator or a substance is the potential gradient. Now when we talk about potential gradient, talk about the value of electric field intensity. You can say potential gradient or electric field intensity because potential gradient is V over D. And you already know, we already saw under electric field intensity between two parallel plates that V over D is equal to electric field intensity. So when they talk about potential gradient, just know they mean electric field intensity because they are the same. Is the potential gradient beyond which a dielectric breaks down. And this value varies for different substances. So that is what we call dielectric strength. Then what about dielectric constant? So another word for dielectric constant is relative permittivity, and is denoted by a symbol epsilon r. Remember, permittivity of free space was epsilon naught. Now relative permittivity is epsilon r. So this symbol will be used more frequently in the calculations of this video. Now, what is a dielectric constant, or what is relative permittivity? So you come as that this is the ratio of the capacitance of a capacitor when the space between its plates is filled with a material to capacitance of the same capacitor when the space between them is filled with a vacuum. So you get a capacitor, then you put a material between them. So this material affects the capacitance of the capacitor. So you get its capacitance, so it can be C1. Then you also get the capacitance when the material, when there's no dielectric and it is free space, so you get also its capacitance. So you get their ratio, and that will be equal to the relative permittivity. So we shall come here and say that if V is the PD across the plates of a capacitor when the space between them is filled with a material, and V0 is the PD across the capacitor plates of the same capacitor when the space between them is vacuum, it implies that C is equal to Q over V and C0 is equal to Q over V0. So the charge will be the same. It is the PD which is changing. So C is the capacitance when there is a dielectric, C0 is the capacitance when there is no dielectric. Therefore, relative permittivity from the definition it will be C over C0. And when I substitute for C and for C0, I'll come up with V0 over V. So these are the two formulas for relative permittivity. One is this one, and we have already seen the definition. Another one is in terms of PD. So that means that you can also define relative permittivity in terms of PD. But remember, previous for capacitance, it was capacitance when the place is filled with dielectric over capacitance when the space is vacuum. But when it comes to PD, it is PD when the space is filled with vacuum over PD when the space is filled with a dielectric. For example, let's see this definition. So dielectric constant can also be defined as the ratio of PD across the plates of a capacitor when the space between them is vacuum. So here I first talk about vacuum. I think you know the difference. For capacitance, we first talked about the material, then we went to vacuum. But here we have to talk about the vacuum followed by the material. So you can continue and say to PD across the plates of a capacitor when the space between them is filled with a material. That is when you're defining in terms of PD. But if you're defining in terms of capacitance, you should remember to first talk about the material, then followed by a vacuum. So the order is very vital. Also, there's this definition which we also saw about capacitance, that capacitance is equal to permittivity over material times area of the plates divided by the plate separation. Therefore, this will be for when there is material, and this when there is no material, when the space is filled with vacuum. Here it will be epsilon naught. So epsilon naught means permittivity of free space times area of the plates divided by the separation of the plates. Now, when we also divide the two, we shall come up with something. So substitute for this and also substitute for this. You realize that this one cancels, and remain with this divided by this, which is here. So that gives us a third definition of relative permittivity. So relative permittivity or dielectric constant, like I told you they are same, can also be defined as the ratio of the permittivity of a material to permittivity of free space. So it has to be material first followed by free space. I think this is more friendly because it is brief. So any of the three definitions is okay, though personally I would prefer this one, which is a little brief. So that means that when I try to make this permittivity of material subject, it will be relative permittivity multiplied by the permittivity of free space. So why do I do that? It is because most times we'll be given relative permittivity, and this permittivity of free space is a constant, meaning that when you're given relative permittivity, it is possible to get the permittivity of a material. So then you have to note that capacitance over capacitor when the medium is dielectric is given by this. This is what I told you, because when they give you relative permittivity, it implies that you can get the permittivity of that medium by multiplying relative permittivity by the permittivity of free space. So with that, we can go through these questions. So question 1 came from UNEB 2019 paper 2 question 10b Roman 2 and says a parallel plate capacitor is charged to 100 volt and then isolated. When a sheet of dielectric is inserted between the plates, the PD decreased to 30 volt. Calculate the dielectric constant of the dielectric. So this is PD when the plates are filled with vacuum, and PD when the plates are filled with a dielectric. Therefore, you shall come and remember that the definition of relative permittivity when the plates are filled with relative permittivity in terms of PD is PD when the plates are filled with vacuum over PD when the plates are filled with a material. Therefore, you shall come and put PD when the plates are filled with vacuum over PD when the plates are filled with the material to give you this as the relative permittivity they wanted. So that is question 1. Question 2 came from UNEB 2017 paper 2 question 10b and says a parallel plate capacitor with plate area this and plate separation this, so this is A, this is D, is connected to a 500 volt supply. Roman 1. Calculate the energy stored in the capacitor. And Roman 2. If the space between the plates is completely filled with oil and the total charge in the capacitor becomes this. Find the dielectric constant of the oil. So that is when there is no dielectric, and this is when there is a dielectric. So Roman 1, capacitance at this stage, it is epsilon naught AD. So epsilon naught is a constant, area was given, and D was given. So come up with this as the capacitance when the plates are filled with vacuum. Therefore, energy stored is a half CV squared. So C is this we have got, and V they gave it to us, so we come up with this as the energy stored. Then part B, they say they put a dielectric. Let's see. So part B, they said if the space between the plates is completely filled with oil, that is the dielectric, and the total charge in the capacitor becomes this, find the dielectric constant of the oil. So you come and say that total charge is equal to total capacitance multiplied by total PD. So total capacitance is now epsilon R C1, because we know that epsilon R is equal to capacitance when there is a dielectric over capacitance when there is vacuum. So when I bring this on this side, I'll come up with this capacitance as epsilon R multiplied by the capacitance when the plates are filled with vacuum. So this is where this one is coming from. Then from there I'll come and substitute. I know Q, R I don't know, epsilon R I don't know it, C1 I know it, and V2 I know it. Therefore my work is to make epsilon R the subject, and to be this, and that's what they wanted. Then question 3 came from UNEB 2003 paper 2 question 9b, and says an air capacitor of capacitance 400 microfarad is charged to 180 volt and then connected across an uncharged capacitor of capacitance 500 microfarad. Roman 1, find the energy stored in the 500 microfarad capacitor. And Roman 2, with the two capacitors still connected, a dielectric of dielectric constant this 1.5 is inserted between the plates of the 400 microfarad capacitor. If the separation between the plates remains the same, find the new PD across the two capacitors. So let's first start with Roman 1, which says find the energy stored in the 500 microfarad capacitor. So for Roman 1, we shall need a sketch for easy illustration. So initially it was this capacitor which was charged to this PD, then it was connected to an uncharged capacitor in parallel. That means that charge flows until PD is the same for both capacitors. Therefore, total charge before connection will be equal to total charge after connection. I believe you already saw this in the previous video. So before connection it will be this times this, which is here. Then after connection you shall first combine these two capacitances in parallel, which is this. Then you multiply by the total PD, which is that. Next is to substitute and make and simplify. Then you make V2 the subject. So that will be the PD. Now that I've got PD, I can get the energy stored in the 500 microfarad. So it will be a half CV squared. C is that and V is that. So we come up with 1.6 joules as the energy stored. So that was Roman 1. What about Roman 2? Roman 2 says, with the two capacitors still connected, a dielectric of dielectric constant 1.5 is inserted between the plates of the 400 microfarad capacitor. If the separation between the plates remains the same, find the new PD across the capacitors. So here we shall come and make a sketch. First, before inserting the dielectric, we already saw that PD is 80 volt. Then what about after inserting a dielectric? So the new PD, we don't know it, so that's why you call it a question mark. Then here this capacitance now becomes epsilon r times the original capacitance without when the space is vacuum. So total charge before insertion is equal to total charge after insertion. So you come and substitute total capacitance before is this plus this, which is here, multiplied by V, PD. Then total charge after is this plus this, which is here, times the PD. So next is to substitute. Then I simplify, after which I'll make V3 the subject. And that's what they wanted. Then question 4 came from UNEB 1997 paper 2 question 10D and says a 2 microfarad capacitor can just withstand a PD of 5000 volts. That can just withstand a PD of 5000 volts uses a dielectric with a dielectric constant 6, which breaks down if the electric field strength in it exceeds this. Find Roman 1, the thickness of the dielectric, and Roman 2, the effective area of each plate, and Roman 3, the energy stored per unit volume of dielectric. So the hint is that capacitance is given by this. I think we already saw this formula, where A is the area, surface area, D is the separation, and epsilon r is the dielectric constant. So here they have helped us by giving us the formula. So just start with Roman 1, the thickness. So first of all, we know that E is equal to V over D, electric field intensity is equal to PD over separation. So come and substitute for electric field intensity and for PD to get their thickness or the separation. That was Roman 1. Then Roman 2, effective area of each plate. So you know that capacitance is given by that formula, so we shall come and make A the subject, then substitute, and then use a calculator to get the area they wanted. What about Roman 3? Roman 3, they want energy stored per unit volume of the dielectric. Energy per unit volume. So energy stored is half CV squared. Substitute for C and substitute for V to give you this. Then the volume is area, cross-section area times D, which gives you, so area is that and D is that, to give you this. Therefore, the energy stored per unit volume, we shall divide the two to give you this as the answer they wanted. Then question 5 came from UNEB 2012, paper 2, question 10C, and says the diagram in the figure below shows an arrangement of 3 capacitors, these ones, of capacitance says these ones, respectively. So it's the diagram. Calculate the total energy stored, Roman 1, in all the capacitors when fully charged. Roman 2, when the space between the capacitors, between the plates of C2 is filled with a dielectric of dielectric constant 1.25. So we shall first start with this one, energy stored when the capacitors are fully charged. So first of all, we have first combined the two capacitances C1 and C2 in series. So if you look at this, this and this are in series. These two capacitances are in series. So we are going to first combine the two by using the special case of product over sum. To come up with this. So when you do that, now the circuit becomes this. I think you realize these ones are now in parallel. So parallel we just add. So we shall combine the two capacitances in parallel to come up with the total capacitance, which is 7.6 microfarad. Therefore, I know total capacitance and I know total PD, so I can get total energy stored. So energy is a half CV squared. So substitute for C and substitute for V to come up with that total energy. So that was Roman 1. Now we shall go to Roman 2. Roman 2 says, when the space between the plates C2 is filled with a dielectric of direct constant 1.25, calculate the total energy. So here they are going to fill it with a dielectric. That means that now the circuit will become in this form. And because there is a dielectric, the capacitance will change. It is now relative permittivity times the capacitance when the space was vacuum. I think by now you know that formula. And when you do that, these two will still be in series. So you have to combine the two. So you come and say that new capacitance of C2 is C6, which is that, and after that we shall combine C6 and C1 in series by using product over sum to give you this. Then from there, when you combine, this is what will happen. We have C3 and C7, but they will be in parallel. So next is to combine C3 and C7 in parallel to get the total capacitance. After getting the total capacitance and we know the total PD, we can get total energy from half CV squared. So substitute for C and substitute for V to give you the energy they wanted. Then question 6 came from UNEB 2004 paper 2 question 9D, and it says, in figure above, C1, C2, C3 are capacitors of capacitances, these ones, respectively, connected to a battery of EMF 100 volt. Roman 1, calculate the energy stored in the system of capacitors if the space between the plates of C1 is filled with an insulator of dielectric constant 3 and the capacitors are fully charged. That is Roman 1. Roman 2, account for the change in the energy stored by an isolated charged capacitor when the plate separation is doubled. So let's start with Roman 1. So for Roman 1, new capacitance of C1, because there's a dielectric now, it becomes dielectric constant times the capacitance if it was vacuum, and to be 9 microfarad. So when I combine the capacitances C2 and C3 in parallel, so I'll come here and realize that these two are in parallel. This and this, they are in parallel, so I have to first combine the two. Therefore, I come and combine by adding them to give you 4 microfarad. And when I do that, I'll come up with this. So initially, this is what happened. We put a dielectric here and the new capacitance is now C4. And after that, after combining these two in parallel, we come up with this circuit. So this C4 and C5 are in series. Therefore, I'm going to combine the two capacitances in series by using the formula of product over sum to get the total capacitance as this. Therefore, total energy is equal to total capacitance multiplied by total PD to give you this as the total energy. That was Roman 1. What about Roman 2? Roman 2, they said account for the change in the energy stored in an isolated charged capacitor when the plate separation is doubled. So here we need something like a derivation, so we shall say energy stored in an isolated charged capacitor is given by that. I have CV squared, where we can substitute for V to give you this other formula for energy. Also, we know that C is equal to epsilon naught AD for an isolated capacitor. Isolated means space between them is filled with a vacuum. So we are going to substitute for C to give you this, and in the end simplify to give you that. Now, since the whole of this is a constant, it implies that energy is proportional to the separation. What does that mean? It means that when the separation is doubled, energy stored is also doubled. And that's what they wanted. So this is just a note for you to easily understand this, that when the separation of the plates is increased, work is done in pulling the plates apart, and this work done is stored as electrical energy between the plates of the capacitor. So this one is just to help you to remember that when the separation increases, work is done and therefore energy also must increase. But the question wanted what happens when is doubled. So you have to go through this and you say when the separation is doubled, energy stored is doubled. Full stop. If they ask what happens when the separation is increased, this is what you would have written. Then question 7 says, question 7 came from UNEB 2000 paper 2 question 10b, and it says a capacitor filled with a dielectric is charged and then discharged through a milliammeter. The dielectric is then drawn halfway and the capacitor charged to the same voltage and discharged through the milliammeter again. Show that the relative permittivity epsilon r of the dielectric is given by this formula, where I and I prime are the readings of the milliammeter respectively. So here we shall need an illustration for you to easily make the derivation. So this is before you displace the dielectric. So when you connect this K to 1, you are charging it. And after that, when you want to discharge, you connect this switch K to 2. It will discharge through this milliammeter, and the ammeter will give a reading or a throw of I. That is before displacing. What about after displacing halfway? So what displacing halfway is still the circuit is like this. So when you connect this K to this, you are charging, and when you want to discharge, you connect this K to 2. It will discharge through this milliammeter and give the reading this. Now, when you displace halfway, there is something funny which happens. If you look at this capacitor, half of it has a dielectric, and half of it does not have a dielectric. What does that mean? It means that this capacitor will be now split into two. One will be having a dielectric, so this one will be a capacitance when there's the dielectric, and this will be capacitance when there's no dielectric. and they will be in parallel. So with that illustration, you can now go ahead and answer our question. So before displacing the dielectric, the capacitance is given by this. I think we know this formula. This is a formula when there's a dielectric in between the plates. Therefore, the initial charge is CV, where C is this and V is here, which is this. So when I combine, I'll come up with this. That is the initial charge, where A is the area of overlap and D is the plate separation. Now what about when the dielectric is withdrawn halfway? So now we have two capacitors in parallel. Therefore, total capacitance will be got by adding. So this is C2. So when I add, I'll come up with, now the area now will be a half A, because it is half. This one is covering half the capacitance and this one is also covering half the capacitance. So simplify, this gives you this and this gives you that. And when I add these ones, you realize that there are some things in common. The whole of this is also found here, because there is this and also this. So we pull it out, and this here remain with 1, here remain with epsilon r. Therefore, the final charge is C prime V. Substitute for C prime and substitute for V. Simplify to give you this. But we know that charge is proportional to current. Therefore, Q initial over Q final is equal to I initial over I final. So I'll come and substitute for Q initial, which was good in previous slide, over Q final, and to be equal to I initial over I final. Then from there you realize that this one is going to cancel, this AV is going to cancel, and this D is going to cancel. So what does that mean? It means that you are going to remain, numerator will remain with epsilon r. Denominator, there is this a half, and there is also this bracket which is here. Then from there I'm going to take the whole of this side and this side, I'm cross multiplying. Then from there I'll bring this to this side to give you this line and open the bracket. Then from there my aim is to make epsilon r the subject, so I'll bring the whole of this side to give you this line. Then epsilon r is common, factorize it out, then make it the subject, and that's what they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on current electricity. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.